Hello guys, welcome back to my channel Gamma Di Gamma. Now this video is untimely because I want to discuss something that's related in linear algebra and stuff. And although I've been doing calculus, I've been doing physics now out of any other math video. I just wanted to take time to explain this concept of reflection along a plane using linear transformations and matrices basically. So let's get started. Okay, so the basic idea goes like this. We have a plane with an equation ax plus by plus cz is equal to 0, and we want to reflect elements along this plane. So for example, if the plane were something like this, I'm assuming this is like a two-dimensional plane sitting in a three-dimensional space. Okay, I mean, my drawing's bad, but apart from that, if we take an element in three-dimensional space, so let me just clarify, we're working in R3 already. So if we have an element in this R3, and usually it's a vector in R3, if we reflect along this plane, so assume that this plane is some sort of a mirror, it will get reflected. Now this is probably not accurate in terms of visual representation, but I hope you get the idea. Now before doing anything, and I hope you're familiar with dot products, let's notice this one thing. If you take the vector ABC and you dot it with x, y, z, you're gonna get 0, because you'll just get ax plus by plus cz, which according to our constraint is 0. And xyz, by the idea of writing an equation of a plane in this way, represents xyz represents an arbitrary point on the plane. Think about it this way. If you have the equation of a line, y is equal to mx plus c, y and x are points, arbitrary points on the line, and this equation is saying that we need to choose x and y in such a way that they satisfy this relation. Moreover, y will equal m times x plus the y-intercept of c. So just like x and y were arbitrary points on the line whose equation we sought to find, x, y, z are arbitrary points on the plane whose equation is given over here. So what this means is that ABC, this vector ABC, and I'm writing in terms of a column matrix, it's actually a vector, I don't know, you can call it A bar or whatever, is perpendicular to every point on the plane, because xyz is an arbitrary point, right? So and if xyz belong to R, because we are working on R3, which means xyz, the vector, is an element of R3. It includes all points on the plane. So this vector ABC is perpendicular to every point on the plane, implying that ABC is perpendicular to the plane in totality. Okay, fine, great news. Now we need to find two other points which are allegedly on the plane, and well, we'll have good reasoning why they have to be on the plane. So take b equals 0, take rather y equals 0 instead of. So if we let y equals 0, the equation becomes ax plus cz is equal to 0. Now we need to choose x and z in such a way that this equation is satisfied. So take x to be c and z to be negative a, because if you plug everything in, ac minus ac is definitely 0. So one solution when y is 0 is x is c and z is negative a. This is one vector that is satisfying the equation of the plane and hence is on the plane. We can do the similar approach if we let z equals 0. If we let z equals 0, our equation just becomes ax plus by is equal to 0. Now we can take x to be b and y to be negative a, and z is 0 according to our condition. And again, this satisfies the equation and is on the plane. So now we have a perpendicular vector to every point on the plane and 2 points on the plane. So somewhat like this. So like call this this vector. This is like this vector. So 2 vectors in the plane and then one vector which is perpendicular to both of them, because since both of them are basically spanning a plane, the plane that we wrote equations for or had equations for in the start, this guy will have to be perpendicular to both of them, because you can think of them as arbitrary points on the plane, and this guy is perpendicular to arbitrary points on the plane. Okay, so instead of our standard basis of 1 0 0 0 1 0 and 0 0 1, if we were to consider these 3 vectors as like a new basis, that basis would be ABC, the perpendicular vector. The order here is not really important. B negative A 0 and C 0 negative A. Fine. And we usually represent a basis like this in terms of a 3x3 matrix, because we consider that to be some sort of mansion of vectors, not like a single column, but it has 3 columns. So 1 0 0 0 1 0 0 0 1 is our standard basis vector S, and our new basis vector, so instead of vector I should say matrix or a system. You can call it a basis system, I don't know, it's terminology. So our new basis ABC, I can write it as a matrix B negative A0 C0 negative A. Fair enough. Now what's the advantage of doing this is, remember we have to talk about reflections. So now if I were to apply the reflection matrix, some reflection matrix on this T, this base, this new basis that's particular to this plane that we defined, think about it, what it's going to do. So if we reflect the vector that's perpendicular to the plane along the plane, it'll just get reflected by 180 degrees. So by 180 degrees reflection, I mean it will become negative A, negative B, negative C. While the other 2 vectors that are inside the plane, if you reflect them along the plane, they'll remain the same because they're lying in the plane. So B negative A0, C0 negative A. Fine. Okay. Now can I express this guy as uh, the vector t, the original like basis matrix that we worked with. I don't know why keep calling it a vector, but the original basis we worked with times some other matrix M. I mean, can we do that? Well, if you just examine a little closely for t to change into this guy after reflection, M will need to be negative 1 0 0 0 1 0 0 0 1, because if you do the multiplication a b c b negative a 0 c 0 negative a, if you do the multiplication, what you get is precisely negative a negative b negative c, b negative a 0 c 0 negative a. That's exactly what we want. So M is just this guy. Now one thing to note is if we put M before the t, if we had mt, then the multiplication would be the transpose of this guy, and we don't want that. So generally when you're working on stuff like this, reflection or change of bases, you have the reflection matrix or the operation matrix. Here it's the operation is reflection times the new basis matrix is equal to the basis matrix times M, which basically tells how much the basis matrix is changing. Okay, now we need to find R. So if we take inverse on both sides, so we have Tm, T inverse. Okay, and what is T? We know T. We had this all along. T is A, B, C, B, negative A 0, C 0, negative A, times the M. What's M? Well, just this weird thing that almost looks like an identity matrix, but it's not because we have a negative one there. Multiplied with the inverse of this guy. So I will calculate the inverse separately, but in the meantime I hope you consider the following. If we interpreted T as the matrix that's taking you from the standard basis to the T basis, it works, because consider some transition matrix from basis S to basis T that will naturally act on basis S, because that's sort of like the input. Basis S is our identity matrix to give us some this new basis matrix, which in our case is ABC, B negative A 0, C 0 negative A. Any matrix times identity is that matrix itself. So transition matrix from standard basis to the T basis is just this T basis matrix itself. That's the essence of linear transformations, because if you want to sort of change coordinates or something like that, bases or stuff, just multiply by that matrix, because if you individually keep track of where this goes, where this goes, where this goes, and write them after you calculate them individually in as columns of a matrix, you'll have the appropriate transformation from that original standard basis to whatever basis you want. And then the P inverse will basically be the transition matrix from T to S. We are undoing the process from S to T, so we'll have T to S, and that will be the inverse of this guy, which exactly we intend to find, because if I write this equation for R, I'll have P from S to T of M and P from T to S. And I'm going to do the calculation for the inverse on a fresh page. See you there. Okay, so we have to invert the matrix T as discussed. So we use this formula for T inverse. 1 over the determinant of T times the adjoint of T. Okay, so determinants can be calculated easily, pretty easily. It's not much of a challenge considering what we did. So the determinant of t, and I hope you use the formula, is a times a squared plus b squared plus c squared. Okay, so now let's go on to find the adjoint. So for that we can consider, say, cofactor of 1 1, cofactor of 1 2 but with a negative, cofactor of 1 3, cofactor of 2 1 with a negative, cofactor of 2 2, cofactor of 2 3 with a negative, and then cofactor of 3 1, cofactor of 3 2 with a negative, cofactor of 3 3. This guy just turns out to be a squared. This will become ab. I'm just doing this quickly so that I don't waste much of your time. AB, here we have negative a squared minus c squared. Here it's a BC, AC again, BC, and a negative a squared minus b squared. So if we put all this together, T inverse basically has the form 1 over a times a squared plus b squared plus c squared, a squared, AB, AC, AB, negative a squared plus c squared, BC, AC, BC, negative a squared plus b squared. Okay, now if we want to plug this back into our formula, that the reflection matrix was T times M times T inverse, and we do the resulting calculations, which are going to look bad. Like we have 1 over a squared plus b squared plus c squared, and the T matrix, which was ABC, B negative A0, C0 negative A, and then the M matrix, which was negative 1 0 0, 0 1 0, 0 0 1, and this inverse matrix. We took the determinant out separate, that's why AB, AC, AB, negative a squared plus c squared, BC, AC, BC, negative a squared plus b squared. And if we do this grotesque multiplication carefully, we just have 1 over a squared plus b squared plus c squared, and this is the reflection matrix that we're going to write. Negative a squared plus b squared plus c squared, negative 2ab, negative 2ac, negative 2ab, a squared minus b squared plus c squared, negative 2bc, negative 2ac, negative 2bc, a squared plus b squared minus c squared. I know this is sort of messy, but I'm sorry for the mess though. That's the reflection matrix we are looking for. Now let's just test this. We had this for a general equation of a plane. Now if we want to reflect along the line y equals x, so we'll need a c to be 0, a to be 1, and b to be negative 1 for that to occur. And if we plug everything into this formulation, we have half, and then 0 2 0 2 0 0 0 0 2, which on dividing will become 0 1 0 1 0 0 0 0 1. And if you just want to test this, take this reflection matrix and let's test this on a test vector, call that x1, x2, and x3. And this is reflection across the line y is equal to x. There's no z, that's why it's a single line now. If we do that, this multiplication will result in x2, x1, x3, and rest assured this is exactly what we wanted, because reflection across the line y equals x interchanges the x and the y coordinates. Y coordinate was x2, that became the x coordinate, which is in the place of x1 now after reflection. So our relation works fantastically. Although the formula is ugly, but it's really powerful, and that's the essence of linear algebra, because you can see just by changing a, b and c we can change the plane of reflection and we can get the appropriate reflection matrix. Then take any arbitrary point, I don't care, any arbitrary point, multiply it properly without making any mistakes with this resultant matrix for that given plane in R3, and you will get the appropriate reflection. So, beautiful formula, and I hope you enjoyed this video. I promised I would make a playlist on linear algebra, and I will, but it's going to take some time, I think, but I will keep posting these untimely videos. So if you have any comments about me not wanting to do this or like wanting to do more of this, please write it down in the comment section. That's it for today, I guess. And before like concluding this video, I just wanted to point out it's ironical that today is a National Boyfriend's Day. I'm single, I don't care, and I couldn't care less. So please like, share, subscribe to my channel, guys. Recommend me to your friends. Spread the word of gamma digamma in the math community. And in the meantime, stay home, stay safe, keep doing math. I will post more content as and when I get time, because my prelims are coming up soon. In like one is like in 3 days, and then there's next week is all packed up. And if I survive the prelims, I'll post more content. So stay tuned and peace out here.